Welcome to a deep dive into a topic that might seem really specialized, but honestly, it underpins so much of our modern world. TIG welding. Imagine like joining metals with almost surgical precision, creating bonds so clean, so strong, they hold together everything from rocket motor cases to, critical stuff in the food industry. That's the fascinating world we're stepping into today. We've got some absolutely fantastic material here, giving us a really detailed look at the ins and outs of TIG welding, which, by the way, in the U.S., you'll often hear called Gas Tungsten Arc Welding, or just GTAW. So our mission for you today is pretty clear. We want to unpack the core characteristics of this very controlled welding process. We'll try to demystify those critical variables that master welders control, often with incredible skill, right? And explore exactly why TIG is the go-to choice for some of the most demanding, highest-stakes applications out there. We'll also look at some challenges, what to watch out for.
Yeah, and what's really fascinating, I think, is how seemingly tiny details in this process can have such a huge impact on the weld quality, the integrity. We'll be connecting the dots, between the science and the actual hands-on application, hopefully giving you a clearer picture of why certain choices get made in this really highly skilled craft.
Okay, let's dive right in then. At its heart, what is TIG welding? How does it actually work?
Okay, so basically TIG welding, or GTAW, it uses an electric arc to create heat and melt the metal. This arc forms between a tungsten electrode, and this is key, it's non-consumable, and the metal part you're welding, the workpiece. But the real magic maybe is the shielding gas, usually argon or helium, sometimes a mix. This gas flows constantly around the electrode and the weld puddle.
Like a protective bubble.
Exactly, an invisible bubble that keeps oxygen out. This prevents the hot tungsten and the molten metal from getting contaminated, which is absolutely vital for a good quality weld.
And tungsten.
Hmm.
That specific choice of metal isn't accidental, is it? It's central to this.
Oh, absolutely central. Tungsten's chosen because its melting point is incredibly high. We're talking 3,370 degrees Celsius, just way beyond any other common metal. So it can handle the intense heat of that arc without melting itself and dripping into the weld pool. Keeps things clean.
Right, so that explains the non-consumable part. Okay, so given this need for precision, it sounds like a welder has a lot of things they need to control, right? Lots of variables. Our sources list quite a few critical ones. Where do we even start?
Yeah, it's definitely a process of control. The main things you're adjusting are the welding current, the current type and its polarity, travel speed, how fast you move the torch. Also, the shape and angle of the tungsten tip, the flow rate of that shielding gas we mentioned, and electrode extension, how far the tungsten sticks out. And each one of these plays a really significant role. They all interact.
Okay, let's break those down, starting with maybe the most basic one. Welding current.
Yeah.
How does adjusting the amps affect the final weld?
Well, weld penetration is directly tied to the current. If your current's too low, the electrode tip just won't get hot enough. You'll get an unstable arc. Maybe it flickers, doesn't really melt the base metal properly.
Not enough power, basically.
Right, but if you crank it up too high, the opposite happens. The tip can overheat, it might even melt or start to erode, and tiny bits of tungsten can break off and fall into the weld. We call those tungsten inclusions.
And those are bad news, I assume.
Oh, definitely bad news. They're usually unacceptable for most quality standards. You don't want bits of electrode in your final joint.
Okay, so current level is crucial. But then you mentioned current type and polarity. This sounds like where it gets really interesting. DC negative, AC DC positive. What are the trade-offs there?
Yeah, this is a really key decision for the welder. For, let's say, most standard jobs, stainless steels, DC negative or DCEN usually gives the best results. With DC negative, about 70% of the heat is focused right on the workpiece.
So it concentrates the energy where you need the melting?
Exactly. This gives you a deep, narrow weld profile. Really good penetration. Plus, the electrode can handle a lot more current this way. A small 3.2 millimeter electrode might handle up to 400 amps. It's efficient. However, some metals, and aluminum and magnesium are the classic examples, they form these really tough oxide layers on the surface almost instantly.
Like a skin?
Yeah, a very stubborn, high melting point skin. It gets in the way of proper fusion. So for those, you need something different. You typically use AC, alternating current, or sometimes DC positive, DCEP. The reason is they provide a cleaning action.
A cleaning action.
Mhm.
How does the electricity clean the metal?
It's pretty cool, actually. With AC, the current switches back and forth, right? So the heat gets split, maybe 50-50, between the electrode and the workpiece. But every half cycle, when the electrode is positive, it sort of blasts away that oxide layer electronically. It clears the path for the weld.
Okay, interesting. And DC positive.
DC positive also gives you that cleaning action. But here, about 70% of the heat is concentrated on the electrode.
Wait, the opposite of DC negative?
Exactly. So it gives you a shallower, wider weld, which can be useful sometimes. But the big downside is the electrode heating up. Its current carrying capacity plummets. You might need a big 6.4 millimeter electrode just to handle 120 amps.
Wow.
And you absolutely need a water-cooled torch with DC positive, otherwise the electrode will just overheat and fail very quickly.
That's a massive difference in current handling. Why does focusing the heat on the electrode reduce its capacity so much? Is it just about melting?
Pretty much, yeah. It's about heat balance. When the heat is mostly going into the workpiece, like in DC negative, the electrode can stay relatively cooler for the amount of current flowing through it. But when you reverse that, and the electrode itself is absorbing most of the arc energy, it just can't dissipate that heat fast enough. It rapidly approaches its own melting point, even with much lower current levels. Physics limitation, really.
Fascinating trade-off.
Yeah.
Okay, so beyond the electrics, the physical movement travel speed, that must be critical too.
Yeah. Oh, absolutely critical. Travel speed affects both how wide the weld bead is and how deep it penetrates. Its effect on width is usually a bit more noticeable, though.
So faster means?
Faster travel generally means less heat input per unit length, so you get less penetration and a narrower bead.
And slower.
Slower means more heat input in one spot, deeper penetration, wider bead. It's a real balancing act. You know, finding that consistent speed is key for a uniform weld. Too fast or too slow or inconsistent, and the weld just won't look right or be as strong.
Makes sense. Now, you mentioned tungsten electrodes, but it's not just one type, is it? Our sources talked about different kinds, thoriated, seriated. What's the story there?
Right, you don't just grab any tungsten rod, you choose based on the job. There are several main types. Pure tungsten electrodes are, well, pure. They're often used with AC for things like aluminum because they form a nice, clean, bald end. But starting the arc isn't as easy, and it's not quite as stable as the alloyed types.
Okay, so what about the alloyed ones? Thoriated.
Thoriated electrodes have a bit of thorium oxide mixed in. This makes a big difference. It helps the arc start easier, makes it more stable, increases the current capacity, and the electrode keeps a sharp point longer, which is good for DC welding. The main catch with thoriated is that thoria is slightly radioactive. It emits alpha particles.
Radioactive. Is that a major concern?
Well, the radioactivity itself is low level, but the dust generated when you grind the electrode tip to shape it, that's the concern. You absolutely should not inhale that dust. So proper dust extraction systems are essential when grinding thoriated tungsten.
Okay, important safety note. Are there non-radioactive alternatives then?
Yes, exactly. That's where seriated and lanthaniated electrodes come in. They contain cerium oxide or lanthanum oxide. They offer very similar benefits to thoriated, easy starting, good stability, high current capacity, but without the radioactivity issue. So they've become really popular replacements, and they work well on both DC and AC.
There was one more. Zirconiated.
Right. Zirconiated electrodes contain zirconium oxide. Their performance is kind of in between thoriated and pure tungsten. They tend to form a bald end like pure tungsten, making them good for AC, but they have a higher resistance to contamination. This makes them ideal for really high-integrity welds, where avoiding any tungsten inclusions is absolutely critical.
So even the alloy choice is about fine-tuning for the specific application and current type. And you mentioned the shape of the tip earlier. That matters too. Pointy versus bald.
Yes, the tip geometry is really significant. For DC negative welding, where you typically use thoriated, seriated, or lanthaniated, you grind the tip to a specific point, a vertex angle. A common rule of thumb is the ground length should be about 2 to 2.5 times the electrode diameter.
And changing that angle does something.
It does. A sharper angle, a smaller vertex angle, tends to give a wider, less penetrating arc. A blunter angle, a larger vertex angle, focuses the arc more, increasing penetration. For AC welding, especially with pure or zirconiated tungsten, you often want that bald or hemispherical end we talked about. You might grind it flat first to reduce the risk of a sharp point breaking off, or you can form the ball deliberately.
How do you do that? Just melt the tip?
Essentially, yeah. You grind it, strike an arc on a piece of scrap copper or something, and carefully increase the AC current just until the tip melts and flows into that nice spherical shape. Takes a bit of practice to get it right.
Precision, even in preparing the electrode.
Okay, let's talk about the shielding gas again. You said argon or helium, sometimes mixed. Does the choice between argon and helium make a real difference? They're both inert, right?
They are both inert, meaning they don't react chemically with the weld, but they have different physical properties that definitely affect the arc and the weld. The most common is argon. Helium, or argon-helium mixes, are used too. Sometimes for specific things like certain stainless steels or cupronickel, you might even add a tiny bit of hydrogen, like up to 5% to the argon.
Hydrogen, isn't that reactive? It is, but in small amounts, it can actually increase the heat and fluidity, improving penetration and sometimes reducing porosity. But that's quite specialized. Comparing pure argon and helium, though, there are key differences.
Like what?
Well, arc voltage and heat. Helium gives you a higher arc voltage, which means a hotter arc.
So better for thick stuff.
Exactly. Good for welding thicker sections or metals that conduct heat away quickly, like copper or viscous metals like nickel. Argon has a lower arc voltage, a softer arc, maybe better for thin materials. Helium's higher heating power is also beneficial for those high thermal conductivity materials.
What about shielding effectiveness?
That's another difference. Weld protection. Argon is heavier than air. So in flat or horizontal welding, it tends to blanket the weld area effectively, needing a lower flow rate, and it resists drafts better. Helium is much lighter than air, so you generally need a higher flow rate to push the air out, except maybe in overhead welding, where its lightness might help it stay up around the weld.
Interesting. And cost?
Availability and cost is a big one. Argon is much more common and cheaper because it's extracted from the air. Helium comes from natural gas deposits, it's less available, and significantly more expensive.
So argon is usually the default unless you need helium-specific properties.
Pretty much, yeah. And related to the gas is the flow rate. Getting that right is critical.
You mentioned that earlier. Too low is bad, too high is also bad.
Correct. Too low, and you don't push all the air away. Oxygen and nitrogen get in, causing porosity, little bubbles in the weld, and contamination, making it brittle. But if you turn it up too high, the flow becomes turbulent. It can actually swirl around and suck air from the surroundings into the shielding gas stream.
Counterintuitive.
It is. So you get the same problems, porosity and contamination. There's a sweet spot, usually around, say, 10 to 12 liters per minute, but it depends on the torch size, the joint type, and conditions.
Okay, now this next one sounds like an extra step. Back purging. What is that?
Back purging is essential, especially for reactive metals like stainless steel, titanium, nickel alloys. Basically, anything sensitive to oxidation, it's about protecting the backside or the root of the weld, the side you're not directly hitting with the torch.
Why does the backside need protecting?
Because it gets hot, too. Not melting hot, usually, but hot enough to react badly with oxygen in the air. It forms oxides, discoloration, often called sugaring, on stainless steel. This oxidation can compromise the corrosion resistance and even the strength of the joint.
So how do you protect it? More argon?
Yes, usually pure argon. You introduce it to the backside of the joint to displace the air. If you're welding pipe, it's relatively easy. You can seal the ends and fill the pipe bore with argon.
What about flat plates?
That's trickier. You might use a special backing bar with a groove for the gas or have someone follow along the back with another purge nozzle. For large tanks or vessels, they sometimes use temporary dams inside, maybe made of soluble paper or inflatable rubber bungs to contain the purge gas just around the weld area. It can get quite complex.
Sounds like it.
And the process. You start with a high flow rate to completely push out all the air, the initial purge. Then, before you start welding, you reduce the flow to a gentle rate, maybe around 4 liters per minute, just enough to maintain that protective atmosphere without causing pressure issues. And you usually keep the back purge going until you've completed at least the root pass and maybe the next layer, until the backside is no longer hot enough to oxidize badly.
Is it always needed?
For high-quality work on reactive metals, yes. Interestingly, though, for basic carbon steels, sometimes you can get satisfactory welds without a specific back purge, though the root might oxidize a bit. Depends on the application's requirements.
Okay, one last variable. Electrode extension. What is that and why does it matter?
Electrode extension is simply the distance the tungsten electrode sticks out beyond the end of the contact tube inside the torch body, the part that delivers the current. You often check it indirectly by measuring the stick out from the end of the gas nozzle, which is typically maybe 2 to 3 times the electrode diameter.
And the effect?
It affects how the electrode heats up and the arc stability. If the extension is too short, the tip might not get properly heated by the current flow before the arc, leading to an unstable, wandering arc. If it's too long, sticking out too far, the electrode tip can overheat because it's further from the cooling effect of the collet and gas flow, leading to melting, erosion, and yes, potentially those tungsten inclusions we keep mentioning. Finding that right stick-out length is part of optimizing the setup for stable performance.
Right, it all connects. So we've covered the ideal setup.
Yeah.
But things can still go wrong. What are the common pitfalls and how do welders avoid them?
Two big ones that come up often are those tungsten inclusions and something called crater cracking. We've talked about inclusions, bits of the electrode getting into the weld. They show up really clearly on X-rays because tungsten is so dense, and they're usually a cause for rejection and quality control. A very common cause is thermal shock, hitting a cold electrode instantly with high welding current.
Like dropping ice into hot water, it can fracture.
Sort of, yeah. It stresses the material. So what's the solution?
Is there one built into the machines?
Yes, thankfully. Modern TIG power sources usually have a feature called current slope up or upslope. When you start the arc, instead of jumping straight to full power, the machine gradually increases the current over a short period, maybe a second or two. This heats the tungsten gently, minimizing that thermal shock and dramatically reducing the risk of inclusions.
Clever. Okay, what about the second one, crater cracking?
Crater cracking is a type of solidification cracking. Some filler metals are more prone to it than others. It happens right at the very end of the weld where you stop. The little puddle left behind, the crater, can solidify too quickly or in a concave shape that creates stress as it shrinks, leading to a crack right in the middle.
Another problem solved by modern machines.
Often, yes. Many machines also have a current slope out or downslope function, sometimes called a crater fill function. When you signal the machine to stop welding, instead of cutting the arc instantly, it gradually decreases the current over a set time.
Ah, so the puddle shrinks slowly.
Exactly. The weld pool gets smaller and shallower progressively, allowing it to solidify more slowly and usually with a flatter, less crack-sensitive shape. It lets you gently tail out the weld.
More elegant control.
Yeah.
Okay, so with all this precision, all this control, all these clever features, where does TIG welding really get used the most? Where does it shine?
TIG is definitely a high-performance, high-quality process. You find it where that really matters. For instance, in autogenous welding, that's welding without adding any filler wire.
Just melting the base metal edges together.
Right. It's used for making longitudinal seams on thin-walled pipes and tubes, often stainless steel or other alloys, typical on continuous production lines. Very clean, very fast for that specific application. Then, for high-quality joints using filler wire, it's essential for thicker pipes and tubing in really demanding industries. Think chemical plants, petroleum refineries, power generation.
Places where failure is not an option.
Precisely. And of course, aerospace. Critical components like airframes, engine parts, rocket motor casings. The integrity requirements there are incredibly high, and TIG delivers that.
So, summing it up, what are the big advantages? Why choose TIG despite the complexity?
The benefits are pretty compelling for those applications. First, it produces superior quality welds. They are very clean, very pure, with extremely low levels of diffusible hydrogen.
Hydrogen, why is that important?
Low hydrogen drastically reduces the risk of cold cracking, which is a delayed cracking that can happen after welding, especially in thicker steels. It's a major issue TIG helps avoid. Second, no spatter or slag. Unlike stick welding or some MIG-MAG processes, there are no sparks flying everywhere and no glassy slag covering the weld that needs chipping off.
Which is good for cleanliness.
Perfect for it. Think food and beverage industry pipework, semiconductor manufacturing. Anywhere, contamination is a big no-no. Third, versatility. You can use it with or without filler metal. It works beautifully on thin sections where other processes might burn through, and for certain joints, it can actually achieve pretty high speeds. Fourth, control. You have such precise control over all the variables, especially heat input. This makes it excellent for controlling weld root penetration, getting that perfect first pass in a joint.
Fifth, material range. It can weld almost anything weldable. Steels, stainless, aluminum, magnesium, copper, nickel alloys, titanium, zirconium, even joining to similar metals. Handles those reactive metals with tough oxides really well, provided you use the right technique, like AC for aluminum.
And finally, the heat source, the arc, and the filler metal addition are independent. The welder controls the arc with one hand and feeds the filler wire with the other in manual TIG.
Giving you more control over the weld pool.
Exactly. Great for delicate work on thin materials where you need just the right amount of heat and filler.
Okay, sounds pretty amazing. But every process has its downsides. What are the limitations of TIG? When is it not the right choice?
That's fair. It's not perfect for everything. The main drawbacks are lower deposition rates. Compared to MIG-MAG or stick welding, you just can't put down as much weld metal per hour with TIG. It's slower for filling large joints.
So not ideal for heavy fabrication.
Generally, no. It becomes less economical for sections thicker than, say, 10 millimeters or maybe half an inch. It just takes too long. It also requires higher welder skill. It's typically a two-handed process, needing good coordination and dexterity. The learning curve is steeper than for MIG, for instance.
What about location? Can you do it anywhere?
That's another limitation. It's sensitive to drafts. Because the shielding gas coverage is so critical, windy or drafty conditions, like outdoors on a construction site, make it very difficult to maintain adequate shielding.
So better suited for workshop environments.
Often, yes. Or requires special screening if used outdoors. Also, those tungsten inclusions can still happen if the welder accidentally touches the electrode to the weld pool or gets the settings wrong. And finally, while AC offers cleaning for oxides, TIG itself has low tolerance for contaminants on the base metal or filler wire. Dirt, oil, grease. They need to be meticulously cleaned off before welding for good results. It doesn't have the inherent digging or cleaning power of some other processes.
Right, so precision comes with the need for preparation and control. What an incredible deep dive into TIG welding. It's so clear now that it's far more than just melting metal. It really is this nuanced blend of art and science where every single variable, from the gas flow to the angle you grind the electrode tip, genuinely matters.
Absolutely. And if you connect this to the bigger picture, it really highlights how critical material science and really meticulous process control are. Think about all the industries we rely on every day: transport, energy, food processing. So much depends on the hidden expertise that goes into making these strong, reliable joints. Understanding these details helps you appreciate the engineering that keeps things safe and performing as they should.
So what does this mean for you listening? Well, maybe the next time you see something made of beautifully welded metal, that shiny stainless steel tank at a brewery, maybe a part on an aircraft wing, you'll have a better sense of the incredible skill, the complex decisions, and the sheer control that went into creating that seemingly simple, perfect bond.
Yeah, and it definitely makes you think, considering the cost, the lower speed for heavy sections, what could be next for TIG? What's the next big innovation that might tackle those limitations, the speed, maybe the skill barrier, while keeping that amazing precision and quality? Could it be, I don't know, more advanced robotics? Smarter autonomous systems, maybe totally new shielding gas concepts or electrode materials we haven't even thought of yet? It's definitely something to mull over.